Alright, let's wrap up this learning target. So, what I want you to do is take a moment and read through these vocab words, be familiar with them. I'm just going to focus on a couple of them here. RAD, R-A-D, is a measure of absorbed radiation, and then how that absorbed radiation affects humans, that's a REM, okay? And then radioactive half-life is what is the amount of time it takes for half of the material to decay into the daughter isotope, to that non-radioactive isotope, usually non-radioactive isotope. Okay. So let's talk about half-life a little bit more. Again, the time it takes for 50% of the atoms of a radioactive substance to decay into a stable isotope. So here at time 0, okay, time 0, we have the whole thing is that radioactive isotope atom, and it's decaying randomly over time, and at some point we're going to get to half as many radioactive materials, and then the other half is that stable isotope. Half of them decayed to something stable. At that point, one half-life has occurred, and then when the time it takes for half of these still radioactive to become stable, that's the second half-life. Okay, let me give you an example. Let's say this is my radioactive substance, okay? And then time is passing and half of it turns into a stable isotope. One half-life has occurred, and we're left with half as much of the original parent radioactive isotope. Now, the second half-life occurs, so half of this will now decay and turn into a stable isotope, and we are left with a fourth of the original amount that we had. Okay, so notice, like, we're left with a fourth of what there was, and that was after reaching the second half-life. Right. Here's the equation that we're going to use to help us with this. Okay, so what percent remains after the first half-life? 50% of the original radioactive isotope remains. What is the remainder after the second half-life? 25% of the original remains at the second. Okay. Fraction remaining, meaning if I want to know how much of that remaining radioactive parent isotope I have, this is going to equal the original amount multiplied by 1/2 raised to small n, and make sure you add this in your notes. So the original amount of that, and then small n is the number of half-life that have occurred. Okay, so how many half-lives have occurred, and that will tell us what we have remaining. Now you're going to need this table while you're taking your test, so be mindful of that. We have the amount of half-life, the type of radiation, and what isotopes we're talking about. And we can use this table to answer questions. Okay, so like this first example problem, we have sample problem number 4. 1 gram sample of tritium, which is our radioactive isotope of hydrogen, is produced. So that's what we're starting with, is 1 gram. That's our original amount. Okay, let's add that so we know that the original amount is 1 gram. What will be the mass of the tritium? So we want to know what we're going to end with. Remaining after 24.6 years. So we need to know that half-life. Well, let's see. One half-life occurs in 12.3 years. So we go from 0 to 12.3, that's the first half-life. And then if we go from 12.3 to 24.6, that would be the second half-life. So that must mean that 2 half-lives occurred. Okay. Okay, wonderful. So now let's plug this into our equation, and we'll equal that original amount multiplied by 1/2 raised to the number of half-lives. So we're going to take that original amount multiplied by 1/2 raised to the number of half-lives, which is 2 in this. And so we're left with 0.25 grams of the tritium. And that makes sense, because if 1 gram is the full amount, right, like the paper, if 1 gram is the full amount, and we have 2 half-lives, then we'll be left with 1/4 of a gram. Okay, so we see this in carbon dating. If we can see how much of the original radioactive isotope is there, then we can determine how much time has passed. As long as we're aware of the half-life, we've used this in radioactive tracers, stuff like that. Okay. All right, now, when we have nuclear bombardment, when we are striking a nucleus in order to split it, this is typically done in like a nuclear reactor, okay, that we are trying to cause these high energy protons to be emitted. And we have the difference here of fission and fusion. And just a reminder that fusion occurs in a star, okay? That we're taking these light elements and we're combining them, and each time that we do, we are releasing energy. And when we release the energy, we're left with something that has a greater mass, a greater density. And then we can combine that with lighter ones, and then we're releasing energy. So that's in stars. Fission is in nuclear reactors. We're taking these really, really large nuclei, and then we're sending neutrons and other really small particles at them to break them into smaller components and to release more neutrons in order to break other nuclei. And we get this chain reaction that even though it's not all that much energy that's released each time, we get this chain reaction, and so we're getting more and more energy with each step, to the point that we even have to have these like neutron absorbers in the cores of these nuclear reactors, because we don't want the reaction to get out of control. Okay. All right, awesome. That is learning target 3. Make sure you get on and finish that assignment.